You know, when you look up at a super tall skyscraper on a windy day, you ever wonder how it just stays up there? Well, the secret isn't just about being strong. The real magic, the true engineering marvel, is that these giants aren't just fighting the wind. They're actually designed to move with it in this kind of carefully choreographed dance. So let's get into it. I mean, it sounds completely backwards, right? We build these things to be these massive monuments of stability. So why in the world would engineers design them to sway back and forth? We're talking sometimes several feet, hundreds of meters up in the air. Well, the answer reveals this fundamental truth about how you survive way up in the sky. And there it is. That's the key. A building that's perfectly stiff, it's also brittle. Think of it like a pane of glass. When it's under extreme pressure, it doesn't bend, it just shatters. So that flexibility, that sway, it isn't a weakness at all. It's the core survival strategy that lets a skyscraper handle the unbelievable forces of the wind. So let's be super clear about this. When a skyscraper sways, it is not a flaw. It's not a sign that something's wrong. It is a fundamental, totally intentional, and absolutely necessary design feature. See, engineers learned a long time ago that to conquer the wind, a building has to first learn how to yield to it. This really lays out the trade-off, doesn't it? A rigid building, it just fights the wind and risks shattering. So you go with a flexible building, which bends, and that's good, but that introduces a whole new problem, oscillation. If it just keeps swaying back and forth, well, that creates its own set of pretty serious dangers. And this brings us to the main villain of our story. It's not just the raw power of the wind that's the problem. It's the wind's rhythm. Because when the wind pushes a building at just the right frequency, a little sway can suddenly escalate into a really violent and dangerous oscillation. That phenomenon? It's called resonance. Okay, so what creates this dangerous rhythm? Well, it's something called vortex shedding. See, as wind flows past a tall building, it doesn't just push on the front. It actually creates these swirling pockets of low pressure, vortices, on the sides. And these vortices effectively pull or suck on the building, yanking it from side to side. So let's just walk through it. The wind hits the building and splits. Then a vortex forms on one side, and that suction pulls the tower. That vortex then breaks off, and almost instantly, a new one forms on the other side, pulling the building back the other way. It's this steady, rhythmic, side-to-side pulling that has engineers up at night. And this is the key challenge right here. For these super tall, slender towers, this across-wind force from vortex shedding can be way more powerful than the direct push of the wind. It's like this invisible sideways dance partner that you absolutely have to manage. So this all leads to the big, critical question. Every building has a natural frequency, right? A speed at which it kind of wants to sway. So what happens if the wind speed is just right, and the rhythm of those alternating vortices perfectly syncs up with the building's natural sway? The answer is resonance. It's this positive feedback loop. I mean, think about pushing someone on a swing. If you push at just the right moment in each arc, they go higher and higher and higher. The exact same thing happens to the building. Each rhythmic pull from the vortices just amplifies the sway, and that can lead to incredibly dangerous oscillation. Okay, so how do you fight something like that? Well, the very first line of defense is the building's skeleton itself. Over the decades, the basic structures that form the backbone of these towers have evolved specifically to give them the stiffness they need to resist these forces. And you can really see the evolution right here. Back in the 70s, you had the bundled tube design of the Willis Tower. It's like a bunch of straws bundled together for stiffness. By the 90s, that evolved into the core and outrigger system. Think of a massive central spine braced by these huge trusses. And for today's giants like the Burj Khalifa, it's the buttressed core, which uses a Y shape where the wings are constantly supporting each other. It's incredibly stable. But brute strength isn't the only way. There's a much more elegant solution. And that's to stop the problem right at the source. Instead of just fighting the wind, what if you could just confuse it? What if you could prevent that dangerous rhythm from ever really forming in the first place? And this is where architecture becomes an amazing engineering tool. By tapering the building, you're changing its width at every level so the vortices can't get into a synchronized rhythm. Twisting the facade does the exact same thing. Even just rounding the corners can mess up the airflow enough to seriously weaken those vortices. And yeah, some buildings even have entire empty floors just to let the wind blow right through them. And this is not just theory, folks. Look at the Shanghai Tower. Its beautiful 120-degree twist is not just for looks. Wind tunnel tests confirmed that this specific shape reduced those side-to-side wind forces by a whopping 24%. And that saved them an estimated $58 million in structural steel. Wow. But even with a super strong skeleton and a shape that confuses the wind, you still need one last layer of defense. Hidden away, usually near the top of most super tall skyscrapers, are these massive devices that basically act like shock absorbers, actively working to cancel out any vibrations that are left. The most famous of these is the Tuned Mass Damper, or TMD. It's basically a giant pendulum. We're talking about a massive weight, hundreds of tons, that's tuned to the building's natural frequency. So when the building sways to the right, the sheer inertia of this huge damper makes it swing to the left, creating a counterforce that cancels out the motion and just eats up that energy. And the effect is pretty dramatic. A typical building has very little natural damping, maybe 1%. But you add a TMD, and you can triple or even quadruple that. It can reduce the accelerations you feel at the top by 40 to 50%. That's literally the difference between feeling totally fine and feeling seasick. And this brings us to the ultimate reason for all of this incredible engineering. The main goal of all these systems, believe it or not, isn't actually to keep the building from falling over. Modern skyscrapers are immensely strong. No, the real challenge is something much, much more personal. That's right, the amazing truth is that the entire design isn't dictated by the limits of steel, but by the sensitivity of our inner ear. A building is considered a failure long before it's even close to being unsafe if the people inside can't live or work in it comfortably. This table just puts it all into perspective. Engineers measure this sway in something called milligauges. Below 5, you feel absolutely nothing. Between 5 and 10, that's the limit for a luxury apartment building where people have to sleep. You get above 15, and it just gets annoying. And once you're over 25, people actually start to feel nauseous and scared. All of that technology, the shape, the skeleton, the dampers, it's all designed to keep that motion way down in the imperceptible zone. So in the end, that swaying you might see in a skyscraper, it's the physical proof of this incredibly sophisticated engineering philosophy. It's an admission that you just can't beat the forces of nature with brute force alone. You have to understand them, anticipate them, and design a structure that can elegantly move in harmony with them. It really makes you wonder, doesn't it? As we start pushing towards kilometer-high towers and even beyond, what kind of new materials, what kind of smart systems and aerodynamic shapes are engineers going to invent? What will the next generation of this incredible dance between our buildings and the atmosphere even look like?